afternoon. This is going to be our second chapter in Weld 1950, stainless steel welding of shielded metal arc. We're looking at page 368 on chapter 12, and as you probably know, chapter 12 is a pretty long chapter, but we're just going to pick up that part that has to deal with stainless steel and some other exotic metals, including hard facing. So turn to 368, and I want you to drop down to where it says stainless steel electrodes at the bottom. Now as we go through here, as I've done in the past, I'm going to go ahead and I'm going to tell you, give you a heads up whenever I want you to highlight something. So I want you to highlight the last of that paragraph there, the last of that column under stainless steel electrodes. And let's read from the book. It says, stainless steel is the popular term for the chromium and chromium nickel steels. It is a tough, strong material that is highly resistant to corrosion, high temperatures, oxidation, and scaling. There is a large variety of stainless steels and electrodes to weld them. Both the base metals and the electrodes are expensive and should be handled with care. And I can certainly attest to that. We have some stainless steel welding electrodes in there that are $10 a pound. And that's just a medium expense on those things. So whenever you are practicing with your stainless steels, make sure you use them to the max. We don't want to have any waste at all on this stuff. And this is also why you practice on carbon steel plate, because it's a lot cheaper than stainless steel. If any of you go on to weld take welding 2660, that is our stainless steel pipe class, at that point we'll finally get around to letting you weld with on some stainless steel pipe and using TIG and stick. But until then, it's just so much more economical to weld on carbon. The arc characteristics, the flow of the metal, all of that's going to be virtually identical. It simply just doesn't have the corrosion resistance that stainless steel does. So, go over to the next page, starting at the top of the page. It says, metallurgically, the stainless steels are classified, and you need to remember these names: martinistic, ferritic, precipitation hardening, duplex, and austenitic. In order to understand the various uses of these steels, it is important that you have an understanding of these terms. A martinistic stainless steel is an air hardening steel containing chromium as its principal alloying element, in amounts ranging from 4 to 12%. It is normally hard and brittle. Martinistic stainless steel requires both preheating and post-heating for welding. If you remember from our discussion of Chapter 3, where we talked about the different phases that steel goes through, I talked about martinistic or martensite, and it's hard, it's brittle, but it's abrasion resistance. And this is a martinistic stainless steel, so it's going to have some of those same qualities and characteristics to it. So you've got to take extreme care whenever you're welding that so that it doesn't crack on you. Our next one is ferritic stainless steel. Now, the thing that stands out about ferritic stainless steel is that it is magnetic. Most people think that stainless steels are not magnetic, but ferritic stainless steel is. So remember that. You'll probably find it on your test. Ferritic stainless steel is normally soft and ductile, but it may become brittle when welded. Preheating and post-heating are necessary for successful welding. Then we have precipitation hardening stainless steel, and you can see in abbreviations there. It's abbreviated pH. pH steel has the ability to develop high strength with reasonably simple heat treatment. The precipitation hardening is promoted by one or more alloying elements such as copper, titanium, niobium, and aluminum. pH steels do not require preheat. So it's the alloying elements that they put in there that allow it to get harder through the precipitation hardening process. They're kind of rare. You won't run into them, probably won't run into them very often. The most common one that you're going to run into is austenitic stainless steel, and we'll get to that in a minute. Duplex stainless steel, DDS, is characterized by a low-carbon, body-centered cubic ferrite, face-centered cubic austenite structure. So again, if you go back to what we talked about in Chapter 3, we talked about the atomic structure. We had face-centered cubic, body-centered cubic, close-pack tetragonal, and I forget what the other one was. So at any rate, we had four that we discussed, and these are two of them. And that's where they get the term duplex, because it has two different phase structures in the steel itself. So it's a duplex steel, and duplex type steels resist corrosion, cracking, and pitting, and have yield strengths twice that of the 300 series. Austenitic stainless steel is the 300 type. Going over to austenite in the next column. As I said before, this is the one that you're probably going to run into the most and you will probably end up welding the most. Austenitic stainless steels contain both chromium and nickel. The nickel content usually ranges from 3.5 to 22%, and the chromium content from 16 to 26%. It is strong, ductile, and resistant to impact. Austenitic stainless steel is non-magnetic when annealed, but slightly magnetic when cold worked. Heat treatment is not necessary during welding. So, looking at this page, what we've discussed so far about the martenites and stainless steel, I've got 1, 2, 3, 4, 5, 6, 7 bullets already in that column to the point where we are right now. Put a bullet by this next one. Selection. Selection of the proper type of electrode for stainless steel welding is critical. A different welding method is required for each type. And all of those different welding methods should be spelled out in the welding procedure specification that you are given or guided with whenever you do this type of welding. It should spell out what rod, what voltage, what amperage, whether it needs to be preheated, whether it needs to be post-weld heat treated. All of those things should be spelled out in your welding procedure specification. And again, I encourage all of you to think about taking welding inspection technology, Weld 2670. It's only offered in the spring, but you'll learn in depth about all of these things. Drop down to the next paragraph. It says the identification numbers for stainless steel electrode classifications are somewhat different from those in the American Welding Society system for carbon steel electrodes. Let me flip on a slide here. Stainless steel electrodes, we have E, and again, just like in the AWS system, the E stands for electrode 308, and then E308L. And you use it to weld 304 and 304L. Now, if you remember from our previous discussions, L means low carbon. So electrode 30L, the 3 means that it's a 300 series stainless steel. And then these last 2 digits tell you about its chemical composition and its electrical characteristics. So you're going to use 308 and 308 low carbon to weld 304 and 304L. They do not make a 304 welding electrode, but they do have a 304 product form. You'll find some of that stuff in like food processing plants and such. Then you have E316 and E316L, and they're used to weld 316 and 316L, and you can see they're matching up. And then 309, they use that to weld stainless steel to carbon in what they call a buttering technique or a sequence bead. What they'll do, and I've had to do this in my career, you might have a piece of pipe coming out, and that piece of pipe might be 347 stainless steel. And you're going to weld that to carbon steel. And here you might have SA106B carbon steel. So how do you weld those two together? Because you don't have any corrosion resistant properties here, and it's too much of a jump to go from carbon to 347. So what you do is you butter the surface of your carbon steel with 347, and then you machine that down to get your new weld surface. And then the 309 acts as a transition surface to make your weldment. And that's one of the main purposes of 309. It's designed specifically to do that sort of thing. Now, this is in your book, table 1214, and it talks about the same thing, but before we go over that, let me read again from your textbook a little bit. The identification numbers for stainless steel electrode classifications are somewhat different from those used in the AWS system for carbon steel electrodes. They are based on the American Iron and Steel Institute, bullet, classifications of metal alloys. Table 1214 shows that. The first digits in the identification number refer to the AISI metal classifications number instead of the tensile strength. You remember out, 70-18, 60-10, those numbers refer to the tensile strength. Here they don't. It refers to the type of stainless steel that it is. Thus, the electrodes in the 308XX and E309XX series are suitable for austenitic stainless steels. And a little later on, you'll see that austenitic stainless steels, or if you remember from Chapter 3, austenitic stainless steels had a 300 series number. And even here it tells you to refer to pages 98 through 103 out of Chapter 3 if you want to review that. Now the last two digits of the electrode identification number refer to the position of welding and the operating characteristics as given in the AWS classification system. E309-15, for example, may be used in all positions with direct current electrode positive. It is a low hydrogen electrode with a medium arc penetration. So you can see that it's a little bit different. And if you look here, Table 1214, identification of stainless steel electrodes. This is the AISI designation number. And 302, 303, 304, 308. And you're going to use 308-15 or 308-16. These are the electrical characteristics, DCEP or DCEN or AC. 309, you're going to weld 309, 15, 309, 16. Cobalt, 309 cobalt. Now, I want you to notice these little numbers, a 2, a 1. Whenever you're dealing with any kind of a code or working with any kind of a book that has these little references, always remember the phrase, the big print giveth and the little print taketh away. So you've got to go back down here and look at the notes. What do the notes say? Note number 1, AISI 303 has additional sulfur added to improve machinability. Use lime type 308-15 when welding. So they're clarifying that a little bit. Number 2, niobium and or molybdenum are added to these coatings to aid in prevention of carbide precipitation or to improve strength at elevated temperatures. So they might add niobium to it, which is another name for columbium. And what that does, carbon steel has a tendency to form iron carbides. And what happens is, I think I explained this in Chapter 3, the iron combines with chromium and they form a carbide which is really hard, but it robs the stainless steel of that chromium prevention. Well, if you put niobium or columbium in it, well, the chromium the iron has a preferential taste for the niobium and columbium, so it will combine with that before it combines with the chromium. Therefore, the chromium remains in the steel and you don't lose that resistance. And going back here again, we have 310. And then you have all these other 310s in here. And you notice cobalt, molybdenum. So there's different little alloying elements mixed in there. 312 would be used to weld 312, so forth, 316. And then finally all the way down here is 347. 347's you have to take special precautions with that. It's a pretty hard, pretty exotic type of stainless steel. Okay, let's go back to your book. On the coatings, on the stainless steel electrode coatings, there's 3 types that you need to remember. There's lime titania, or titania. And that's all you need to remember on that. They have 3 different types of coating. Flip the page. It says the lime type covering is designated for DCEP only. These electrodes produce welds that have a convex face and are desirable for root passes in which a full throat section prevents cracking. I'm going to skip down this because I've got some things highlighted in here that I think are important. The coating also produces a flux that drives the impurities from the weld, thereby ensuring a weld that is free of porosity and has the mechanical properties and corrosion-resistant properties expected. The Titania type covering is designed for either alternating current or DCEP, produces a smooth arc with fine bead appearance, and there's very easy slag removal. One thing about welding with stainless steel, by now you've welded a little bit of it, and you see that it produces a pretty thick black, glossy type of slag, and it's vicious. It seems to just pop off unexpectedly and head for your eyes. So always make sure that you're wearing face protection whenever you're working with that. The Titania type covering is designed for either alternating current or DCEP, smooth arc, la-da-da. They produce slightly concave welds that require a minimum of cleaning, grinding, and polishing. And these electrodes are the EXX-16 classification. Then electrodes with lime titania covering may be used with DCEP or DCEN. And they are all position electrodes. They weld the straight chromium ferritic and chromium molybdenum stainless steels, and to some extent the chromium nickel austenitic stainless steels. So that's about it on the stainless steel portions. Okay, hard facing. We had a little technical difficulty there, so if it seems like we jumped a little bit, we really didn't. Hard facing, bullet. I want you to understand what hard facing is. Hard facing is the deposition of an alloy material on a metal part by one of several welding processes to form a protective surface. So read about abrasion, impact, and corrosion. That next paragraph, the second sentence reads, the wear-resistant material is applied only to those surfaces of a component where maximum wear takes place. So you're not going to cover up the entire surface of something, you're just going to put it where it's needed. Good example of that is a bucket when they're welding, when they're doing dirt work, and the teeth will drag across the ground and dig in. They're exposed to an awful lot of wear, so you're going to butter those teeth up sometimes, and that'll help to reduce the wear on that. But you don't have to butter the entire bucket, or take the curve of the bucket. You might want to build up the curve of the bucket where it's going to be dragging across the ground, but you don't have to build up the wear on the depth of the bucket, and so forth. Over into the next column. Top of the column says there are many different kinds of hard-facing materials. Generally, they have a base of iron, nickel, copper, or cobalt. Alloying elements may be carbon, chromium, molybdenum, tungsten, silicon, manganese, nitrogen, vanadium, and titanium. Bullet, the alloying elements form hard carbides that contribute to the properties of the hard-facing metals. Now, we just talked about carbides with iron and chromium, an iron carbide. Hard, right? And corrosion resistant. Not corrosion resistant because it robs it, but here they're alloying them with other things, so we're still forming carbides, different types of carbides that provide that corrosion resistance. I keep wanting to say corrosion resistance, that provide that wear resistance of the hard facing. Now, a high percentage of tungsten or chromium with a high carbon content forms a carbide that is harder than quartz. So you can see that depending on the element that they are combining with, you can get different degrees of hard facing. Now, there's ferrous and non-ferrous types of hard facing. There's three types of ferrous, the austenitic steel electrodes, and they contain chromium, nickel, and iron. They have manganese, hard surfacing, and then dropping down a little bit further, it says the stainless steel types of hard facing electrodes are used for corrosion-resistant overlays and for joining or build-up purposes. Certain types are good heat-resistant alloys and serve for surface protection against oxidation up to 2,000 degrees. Then we have martinistic steel electrodes. The carbon in the martinistic steel is the major determinant of their characteristics. These steels are inexpensive and tough. The alloys with little carbon are tougher and more crack resistant than the types with greater amounts of carbon. You remember we talked about in chapter 3, we talked about low carbon, medium carbon, and high carbon steels. The more carbon content, the stronger it is, the harder it is, but the more brittle it is. Same thing here. So they're telling us that if you have a little bit of carbon in there, they're going to be tough. If everybody remembers what toughness is, it's where it can bend but not break. So it's still pretty strong, bends but not breaks. But as you increase that, then it's more susceptible to cracking. Over on the next page, iron electrodes. Iron-based alloys with high carbon content are called irons because they have the characteristics of cast iron and are used for facing heavy cast iron machinery parts. Then we drop down to the non-ferrous alloys. All you really need to do here is remember the names. There's cobalt-based surfacing metals, composite tungsten carbide materials, copper-based surfacing metals, and nickel-based surfacing metals. So you may get a question where I'm going to ask you to fill in the blank, name me one of these types of non-ferrous surfacing materials. Then aluminum electrodes, as in chapter 3, we're going to hit aluminum pretty hard. There'll be a number of questions coming out of here. First one is a bullet. It says aluminum is the most widely fabricated metal after steel. Okay? Its popularity is due primarily to such factors as its wide availability, strength, lightweight, good workability, and pleasing appearance. Next page. The high strength, liquid, and airtight joints now produced at high speeds in welding aluminum have extended the use of this lightweight material for freight cars of all types. Tank cars, hopper cars, ships, barges, trucks, piping, and many other industrial applications. That's a bullet. The major alloying elements used in aluminum electrodes are magnesium with zinc and with or without magnesium, manganese, and silicone with or without copper. That's a bullet. The two types of covered electrodes generally available and used a great deal are the E1100 and 443 alloys. That's a bullet. And if you remember, I talked about 443 last time as being a very popular aluminum. And here we have a covered electrode that you can actually use to weld 443. And we have some of these electrodes if you'd like to experiment with them. Let's see. Now this is important, and this is a bullet. Alloy E1100 is commercially pure aluminum, giving a weld deposit with a minimum tensile strength of 12,000 psi. Alloy 4043 contains approximately 95% aluminum and 5% silicone. It has an ultimate tensile strength of 30,000 psi. So simply by adding 5% silicone, they've more than doubled the amount of tensile strength that you have in that aluminum. The 4043 electrode is a general purpose wire. It gives better fluidity during welding than the 1100 electrode. And those of you that take gas metal arc welding later on will get a chance to weld some aluminum using the gas metal arc process. The same goes for gas tungsten arc welding. We'll do some of that, but we also have some shielded metal arc welding electrodes that you're welcome to try. In applications where corrosive factors are important, an electrode should be selected that has a composition as close to that of the base metal as possible, and that's a general rule whenever you're doing that. Drop to the next paragraph, and it's a bullet. Ductility and cracking, known as hot shortness, are problems in the welding of aluminum. If you remember back to chapter 3, I talked about how when you're welding aluminum, it doesn't change color. And if you don't support it and you're welding along, it can get too hot and just suddenly, for no apparent reason, fall out on you. It's lost all of its tensile strength, and it just falls out. And you got a big old hole staring at you. That's a result of hot shortness. Specialized electrodes, bullet, remember Inconel, nickel copper alloys, Monel, age hardenable Monel, high nickel alloy filler metals. I'm probably going to ask a question concerning Monel or Inconel because they're very common in the workplace, particularly in high heat applications and pressure piping. As far as the copper electrodes go, if you look at where it says ECUSI in parentheses for copper silicone alloys, and then down below that it says ECUSN-A for copper tin alloys, and it's continued over on the next page with copper nickel, ECUNI. You can tell from what they're talking here, ECUNI. Again, the E stands for electrode. Cu is the chemical designation for copper. Ni is the chemical designation for nickel. So study those, because you're going to have a question in there where I'm going to throw one of those in, and I'm going to ask you to tell me what these chemical designations mean, to identify the electrode based on that. Let's see. Let's go to the last paragraph on this topic where it says the selection of the proper type of electrode for a particular welding job is vital to the successful completion of the job. A welder will never be in a position of knowing all there is to know about the various types of electrodes. You are urged to consult the various welding suppliers, catalogs, and the excellent material available through the American Welding Society in order to develop a comprehensive understanding of the differences between and uses of electrodes. Now I'm going to ask kind of a generic question on that paragraph, so read that a little bit more thoroughly than what I've just mentioned. It may be something in context in relationship to a WPS, welding procedure specification, so keep that in mind. And that is all for this particular section. It's going to be short. It will be 15 to 20 questions. That's an awful lot of questions come out of 6 pages. If you don't understand anything, get with me and I'll help to explain it a little more clearly. Thank you.